Welcome to Night Watch Observer. It's good to have you here tonight, wherever you happen to be. Maybe you're lying in bed with the blankets pulled up and the lamp still glowing soft and low in the corner. Maybe you're on a couch with the room gone quiet around you, or on a long train ride watching the dark slide past the window. Wherever you are, settle in. There's nothing you need to do for the next while except breathe slowly and let your shoulders drop a little. You don't have to follow every word. You don't have to remember any of it. If you drift off somewhere in the middle of all this, that's perfectly fine. The story will still be here, and so will I, and the things we talk about tonight have been quietly happening for almost 50 years without anyone watching. They'll keep happening whether you're awake for them or not. That's part of what makes them so peaceful. And before we begin, just a small thing. If you find these slow journeys helpful, if they help you let go at the end of a long day, a gentle like and a subscribe really do mean a lot to a small channel like this one. Small creators like me lean on that more than you'd think. To those of you who've already subscribed and keep coming back night after night, thank you. Truly, you're the reason I keep making these. And I'm curious, in that lazy, half-awake way, where in the world are you listening from tonight? What time is it in your corner of the dark? Leave it down below if you feel like it, before your eyes get too heavy to type. There's no rush. There's never any rush here. Now, let me try, as I always try, not to make this so interesting that it keeps you awake. Though if it does, well, at least you'll have learned something beautiful before morning. A fair trade, I think. So let me start with a strange and quiet fact. And I want you to just hold it gently in your mind for a moment, like a warm stone. Right now, as you lie there in the warmth of your own room, with your own heating ticking somewhere in the walls, and your own breath misting faintly if the window's open, there is a machine drifting through the coldest place that human beings have ever reached. It is so far away that the number almost stops meaning anything. And it has never, in nearly 50 years, been cold inside. Think about that for a moment. The coldest place we have ever touched, and the inside has stayed warm the whole time. The machine is called Voyager. There are actually two of them, twins, launched in the same year. But tonight we'll mostly follow the one that has gone the farthest, the one we call Voyager 1. It is at this moment more than 160 astronomical units from the Sun. And I should slow down and tell you what that means, because the words go by so easily and they hide something enormous. An astronomical unit is just the distance from the Earth to the Sun, that's all it is. The whole span of our daytime sky, the entire reach of sunlight that warms your face on a summer afternoon, that one trip from us to our star, that's a single astronomical unit. And Voyager 1 is more than 160 of those distances away, stacked end to end. One sunbeam length after another, 160 of them and more, laid out into the dark. In plain kilometers, it is over 24 billion of them, 24 billion. A number so large that your mind sort of slides right off the surface of it, and that's all right. You're not meant to truly feel a number like that. Nobody can. But maybe try it this way instead. Imagine the fastest thing you know, a jet tearing across the sky, leaving a thin white scratch behind it. Now imagine that jet flying without ever landing, without ever stopping for fuel, day after day, year after year, for longer than your whole life. It still wouldn't get there. It wouldn't even come close. That's how far away this little machine is, out past everything, out past the planets, out past the place where the sun's wind finally gives up. Because Voyager has done something almost no human-made thing has ever done. It has left, truly left. There's a boundary out there, a sort of invisible shoreline where the sun's influence finally fades into the influence of the rest of the galaxy. Scientists call it the heliopause. You can think of it as a vast, slow bubble that the sun blows around itself, a bubble made of solar wind, a constant whisper of particles streaming outward in every direction. And that bubble has an edge, a place where the sun's whisper finally goes quiet and the deeper silence of interstellar space takes over. Voyager 1 crossed that edge. It passed through the heliopause and out into the space between the stars, into the true interstellar medium, the stuff that fills the dark between one sun and the next. It did this in the year 2012. So for over a decade now, this small craft has been sailing not through our sun's little neighborhood, but through the open sea beyond it. The first thing we ever built to do that. And out there, it is cold. Cold in a way that's hard to even put words around. You see, the warmth you feel from the sun, the warmth on a windowsill in the late afternoon, the warmth that thaws frost off the grass in the morning, all of that comes from being close. We are bathed in it. We don't even notice it most of the time, the way a fish doesn't notice water. But sunlight fades with distance, and it fades fast. By the time you get out to where Voyager is, the sunlight has thinned to something like a 25,000th of its strength here. In some reckonings even fainter, a 40,000th. Let me try to make that real for you, gently. Imagine the sun, that great blazing thing that lights up our entire sky, that you cannot even look at directly. Now imagine it shrunk down, dimmed down, until it is barely brighter than the brightest star you can see on a clear night. Just a sharp little point of light among all the others. No warmth from it at all. No glow you could feel on your skin. It is, for all practical purposes, just another star out there, and Voyager floats among them, a tiny cold speck in an endless freezing dark. An object sitting out there, with no help, would settle to a temperature far, far below freezing. Below the freezing point of water, yes, but more than that, below the freezing point of every fluid the spacecraft carries, below the point where its electronics would simply seize up and stop. The whole machine should be a frozen, dead lump of metal, drifting silent forever. And yet, the inside of Voyager has never gone cold. Not once. For nearly 50 years, in the coldest place we have ever reached, its little heart has stayed warm. Its instruments have kept their temperature. Its fuel has stayed liquid. Its radio has kept whispering home. How? How is that possible? In a place that cold, with the sun reduced to a pinprick, with no warmth coming from anywhere outside, how has this small thing stayed warm for half a century? That's the question we're going to drift through tonight. Slowly, one soft piece at a time. And the answer is stranger and more beautiful than you might guess, because the very thing that keeps Voyager alive is something that, by every normal measure, looks like a flaw, a waste, an inefficiency. The thing that should be a problem turns out to be the whole secret. But we'll get there. We have all night. Now here's the first thing I want to gently take apart, because almost everyone gets it wrong, and the title of tonight's story even gets it wrong on purpose, just so we can put it right together. People say Voyager runs on a nuclear battery. And it's a lovely phrase, it sounds right. It conjures up something powerful and a little bit mysterious. But here's the quiet truth, the one almost nobody stops to notice. It isn't a battery, not in any real sense of the word, not at all. Let me explain what I mean slowly, because this is where the whole story actually opens up. When you think of a battery, what do you picture? Maybe the little cylinders in a flashlight or a remote control. Maybe the slim slab inside your phone, the one you plug in every night so it fills back up while you sleep. And that's the key thing about a battery, isn't it? It holds a charge. It stores energy that was put into it somewhere else, and then it slowly gives that energy back. And when it's empty, you refill it. You plug it in. The energy flows back in from the wall, from the grid, from a power station somewhere far off, burning coal or spinning a turbine in a river. A battery is a bucket. You fill the bucket, you carry it somewhere, you pour it out, and then you go fill it up again. But out where Voyager is, there is no wall to plug into. There is no grid. There is no power station, no sunlight worth catching, nothing to refill any bucket with. If Voyager carried a battery, an ordinary battery, even an enormous one, it would have run dry within weeks of launch and gone silent decades before you or I were even thinking about it. There is no recharging out there, none. The energy it leaves home with is, in a sense, all it will ever have. So whatever is keeping it alive cannot be a battery because nothing is filling it back up. And here's where the reframe gets even stranger, even quieter. The thing inside Voyager doesn't store energy at all, it makes it. Continuously. On its own. Without anyone putting anything in. There is no charging port. There is nothing being filled. And here's the part that I find almost peaceful in its simplicity. The part that makes engineers smile a little when they explain it. There are no moving parts, none. Nothing spins, nothing pumps, nothing turns or churns or whirs. There is no engine in the way you'd picture an engine, no pistons, no fans, no blades. There's no reactor either, no glowing core that has to be controlled and cooled and watched. None of the drama you might imagine when you hear the word nuclear. None of that. What's actually inside is, in the simplest terms I can give you, a lump of metal that glows red hot all by itself and stays glowing for decades, and a clever little trick that turns that glow into electricity. That's it. That's nearly the whole thing. A piece of warm metal and a way to drink the warmth. I know that sounds almost too simple. We'll take it apart, piece by gentle piece, over the next while, and you'll see exactly how a glowing lump of metal turns into the power that runs an interstellar probe. But hold on to that image for now, because it's the true heart of the whole story. Not a battery, not a bucket of stored charge waiting to run dry. A small, patient source of heat that has been quietly burning for almost 50 years, with nothing to refuel it and nothing to refill it, because it never needed refilling in the first place. So if it isn't a battery, what is it actually called? What's the real name for this strange little heart? It has a wonderful mouthful of a name, and I'm going to give it to you in full, and then I'll translate it. The way I always do, so it stops being intimidating and starts being friendly. It's called a multi-100-watt radioisotope thermoelectric generator. Let that roll past you slowly. Multi-100-watt radioisotope thermoelectric generator. The people who work with these things mercifully just call it an RTG, and we'll do the same most of the time so your half-asleep mind doesn't have to carry the whole phrase around. But let me unwrap that name for you anyway, because every piece of it tells you something true. Multi-100-watt. That part just describes how much power it makes, a few hundred watts, and we'll come back to exactly how much in a moment. Radioisotope. That's the fuel, a special kind of material that gives off heat all on its own, and we'll talk gently about what that material is and why it glows. Thermoelectric, there's the trick I mentioned. Thermo meaning heat, electric meaning, well, electricity. A way of turning heat directly into electricity with no spinning, no moving, nothing churning. And generator, because that's what it does. It generates. It makes power, fresh, continuously, rather than storing it the way a battery would. So the name itself is the whole truth hiding in plain sight. A radioisotope giving off heat, a thermoelectric trick turning that heat into electricity, a generator making power rather than holding it. Not a battery anywhere in the name, you'll notice, because it isn't one. And here's a lovely detail that I want to slip in gently because it surprises almost everyone. Voyager doesn't carry just one of these, it carries three. Three of these multi-100-watt RTGs working together, all on one craft. Three glowing hearts, not one. And they're not tucked away deep inside the spacecraft either. They're held out, away from the body of the craft, on a long arm, a boom, that swings them out to one side, Picture, if you like, someone holding a warm and faintly radiant thing out at arm's length, keeping it close enough to use but far enough away that it doesn't disturb anything. That's roughly the idea. The RTGs are kept out on that boom for a good reason, because the spacecraft is covered in delicate, sensitive instruments built to listen for the faintest whispers of particles and fields out there in the dark, and the RTGs, being what they are, would interfere with that listening if they sat too close. So the engineers gave them their own little outrigger, a deployable boom that unfolded after launch and swung the 3 generators safely out and away, close enough to power the heart, far enough not to deafen the ears. And this design, these particular multi-100-watt units, this was the very first time that exact design had ever been flown in space. Voyager was the maiden voyage in more ways than one, the first to carry these specific generators out into the dark, a brand new heart for a brand new kind of journey. Now let me give you the number, the amount of power, because it's one of those numbers that becomes more astonishing the longer you sit with it. When Voyager left Earth back in 1977, those 3 RTGs working together produced, all in, somewhere around 470 watts of electrical power. 470 watts. Let me make that real for you the way you'd feel it in your own home. Think about the lights in a single room. A few bright bulbs. The kind of light you might have on right now, glowing softly somewhere near you. 470 watts is roughly the draw of just a handful of old household light bulbs. Not the whole house, not even the whole room in some cases. Just a few bulbs worth of power. And with that, with no more electricity than it takes to light a few bulbs over a reading chair, this small machine has run everything. Its computers, its radio, calling all the way home across that impossible distance, its instruments sensing the space around it, its heaters keeping its own blood from freezing. Everything. An entire interstellar explorer, the most distant thing our species has ever made, all running on less power than you might use to light the corner of a living room while you read before bed. There's something almost unbearably tender about that when you sit with it. We tend to imagine that doing something this enormous, reaching this far, lasting this long, must take enormous power. Roaring engines, vast energies, the kind of force that shakes the ground. But no, out there, in the silence between the stars, the whole miracle runs on a few bulbs worth of quiet electricity, sipped slowly from 3 small glowing hearts. It doesn't roar, it barely hums, it just keeps going gently, faithfully on almost nothing at all. And remember, that 470 watts was at the very beginning, at launch, when everything was fresh and full and new. That number, as you might already be sensing, has not stayed where it started. It has been slipping slowly, quietly, year after year after year, the way warmth fades from a stone after you carry it in from the sun. We'll follow that fading carefully. Later tonight, we'll watch the number come down, because that slow fade is really the deepest part of our story, the part with the most feeling in it, the part where engineers, very gently, very deliberately, begin making hard choices about what to let go of so the rest can live a little longer. But not yet. Don't worry about the fading yet. For now, just hold the warm beginning in your mind. 3 glowing hearts on a boom swung out into the dark. 470 watts, a few bulbs worth, lit in 1977. Enough to run a whole explorer to the edge of everything and beyond. And I want to come back, before we drift on, to that quiet paradox we started with, because now you can feel the shape of it forming, the coldest place we have ever reached. Sunlight thinned to a pinprick, a temperature out there that should freeze the whole craft into a silent, lifeless lump. And in the middle of all that cold, 3 small hearts glowing red hot, never refilled, never recharged, simply burning on their own, patiently, the way they have since before many of us were born. That's the thing keeping the inside warm. That's the answer beginning to take shape. Not a battery running down, a source of heat, a maker of warmth that needs nothing from the outside world to keep going. And the heat, the heat is the secret. We'll spend a good while later tonight on exactly why the heat matters so much more than the electricity, why the part everyone thinks is wasted is actually the whole point. But you can already feel the edge of it, can't you? In a place this cold, a thing that simply will not stop being warm is the most precious thing of all. So let's settle a little deeper, now that you have the shape of it. A small machine, more than 160 sunbeam lengths from home, out past the edge of the sun's bubble, sailing the dark between the stars. 3 glowing hearts on an outstretched arm, burning quietly with no fuel line and no charger and no way to refill, making their few 100 watts the way they have for nearly 50 years. Not a battery. Never a battery. Something far older and far simpler, and in its way far more wondrous. And inside, against all reason, against the killing cold of interstellar space, it has stayed warm the whole time. Every single night, including this one, while you lie there listening, it is out there, glowing faintly, holding its own small warmth against the dark. We've only just begun to understand how. We haven't yet opened up those glowing hearts to see what's actually inside them, what strange material burns there without flame, why it glows red hot for decades without ever being lit. We haven't yet seen the clever 200-year-old trick that turns that glow into electricity, a trick discovered long before anyone dreamed of spaceflight. And we haven't yet faced the gentlest and saddest part of all, the slow fading, the careful letting go, the way clever, devoted people have spent decades deciding, piece by piece, what to switch off so that the heartbeat can carry on. All of that is still ahead of us. There's no hurry to reach it. We have the whole night, and the night is long, and Voyager isn't going anywhere fast. It's been drifting at a steady, patient pace for half a century, and it will keep drifting whether we hurry or not. So we won't hurry. We'll take it slow, the way it deserves, the way you deserve, here in the quiet with the lamp low and the dark soft around you. Let yourself sink a little further into the warmth of wherever you are. Let the number 24 billion become just a feeling instead of a figure, the feeling of something very far away and very faithful, still warm, still whispering, still alive. And let me carry you a little deeper into the story, slowly, gently, toward the heart of those 3 glowing hearts and the strange burning material that lives inside them. Now, before we go any further, let me say something simple, and then I'll let it rest. If you're enjoying this slow drift into the dark, a gentle like and a subscribe really do help this little channel keep going. Small creators like me lean on that more than you'd think. And to those of you already here, already subscribed, already part of these quiet nights, thank you. Truly, I'm glad you came back. Before we move on, I'd love to know, where in the world are you listening from tonight? What time is it in your corner of the dark? Picture it for a moment, your city, your room, the hour glowing somewhere nearby. And then let it go and come back here, with me, with Voyager, somewhere out past everything. So, let's talk about what this thing actually is, because the word we keep reaching for, the word everyone reaches for, is wrong. We call it a battery. The nuclear battery that kept Voyager alive. It's a lovely phrase, it just isn't true. Think about what a battery really is, the kind you know, the little cylinder you slide into a flashlight, the slab inside your phone. A battery stores energy. You fill it up, you draw it down, and when it's empty, you plug it in and fill it up again. That's the whole idea of it. Storage, charging, a reservoir you dip into and refill. It's a bucket of energy with a lid. Voyager has nothing like that. There is no bucket, there is no lid. Nothing on board fills up, and nothing ever gets refilled. There's no cord to plug in 24 billion kilometers away. There's no sunlight to catch, not out there. There's no reservoir quietly waiting to be topped off. The very idea of charging it is meaningless. It cannot be charged. It was never going to be charged. It simply isn't that kind of thing. And here's the part that makes people lean in a little. It doesn't move, not inside. We picture machines as things that spin and turn and rumble, gears meshing, pistons rising and falling, some engine somewhere doing the loud work of being alive. Voyager's power source has none of that. No reactor humming away, no fission, no chain reaction, no controlled explosion held carefully in check, no turbine, no spinning anything, no moving parts at all. Let that settle for a moment because it's genuinely strange. The thing that has kept a spacecraft alive for nearly 50 years, across the entire solar system and out into the space between the stars, has no moving parts. Nothing wears out from friction, nothing grinds. There's no motor to seize, no pump to fail in the ordinary mechanical way. It just sits there, quiet, still, working. So if it's not a battery, and it doesn't move and nothing charges it, what on earth is it? What is actually out there holding that small warmth against the cold? It's three of them, first of all, not one, three. We keep saying battery, singular, as if there were a single source tucked away inside, but each Voyager carries three separate power units and they have a name, a real one, a wonderfully specific mouthful of a name. They're called multi-100-watt radioisotope thermoelectric generators. Say it slowly and it almost unfolds itself. Multi-100-watt because that's roughly the scale of power they make. Radioisotope because of what burns inside them. Thermoelectric because of how they turn that burning into electricity. Generator because that, in the end, is the job. Multi-100-watt radioisotope thermoelectric generator. People shorten it mercifully to MHWRTG. We'll do the same. But it's worth hearing the full name once, the way you'd read someone's full name on a letter, because Voyager was the very first craft to ever fly this particular design. These three little units were a kind of debut, and they aren't tucked deep inside the spacecraft, buried among the delicate instruments. They're held out at arm's length. Voyager has a long arm reaching out from its body, a boom, and the three generators ride at the end of it, swung away from everything sensitive. There's a reason for that, and we'll come to it. The way the heat and the faint radiation that pour off them are kept at a polite distance from the instruments trying to measure the universe. But picture it for now. The spacecraft, its big dish antenna, always turned faithfully back toward home. And off to one side, on a slender boom held out into the dark, three small generators, glowing. Glowing, that word again. I keep using it, and I haven't yet earned it, so let me at least begin to. These generators don't burn fuel the way a fire does. There's no flame out there, no oxygen to feed one anyway. And yet inside each unit, something sits genuinely visibly hot, not warm, hot. Hotter than an oven, hotter than molten metal in places, a heat that would glow a dull, steady red if you could somehow stand beside it in the dark and look. It has been glowing like that since 1977, without being lit, without being fed, without ever once going out. We'll get to exactly why, to the strange material that does this, and the long, quiet physics behind it. For now, just hold the image. Three small hearts on a boom, glowing red against absolute black, and they've been glowing for 48 years. Now here's a number that surprises almost everyone. When Voyager left the Earth in 1977, all three of those generators together, all that glowing, all that astonishing engineering, produced about 470 watts of electricity. 470 watts, that's it. That's the whole power budget of an interstellar spacecraft. Sit with how small that is. 470 watts is the draw of a few household light bulbs. Not the dim, efficient little bulbs we mostly use now, but it's still, fundamentally, a handful of bulbs worth of power. You could run a couple of bright old-fashioned lamps on it. A modest hairdryer pulls more. Your kettle pulls far, far more in a single roaring minute than Voyager has ever had to work with at once. And on the power of a few light bulbs, this spacecraft did everything. It powered the computers that steered it. It powered the radio that called home. It powered the instruments that studied Jupiter's storms and Saturn's rings, that found moons no one had ever seen, that measured the wind blowing off the sun, and, eventually, the strange new quiet beyond it. It kept itself warm. It kept itself pointed at Earth. All of it, all of that history ran on less power than you'd use to brighten a single small room. There's something almost unbearably gentle in that when you let it land. We imagine the great achievements of exploration as things of enormous force. Roaring rockets, yes, those are loud and violent and huge, the part everyone remembers. But the rocket only threw Voyager out the door. Everything after that, the whole long life of it, the decades of faithful work, has been powered by a quiet glow, no brighter in energy terms than a few bulbs left on in an empty house. A small, steady warmth doing patient work in the dark for a very long time. So that's the shape of what we're dealing with. 3 glowing generators on a boom, no moving parts, nothing that charges, not a battery, not really, not in any way that matters. A few light bulbs worth of power, drawn not from sunlight or storage, but from something burning slowly and silently inside, turned into electricity by a trick we still haven't looked at. And already a question is forming. I can feel it forming in the quiet. If nothing moves and nothing charges and there's no reactor and no flame, then what is that glowing material? What is it that can sit red hot for half a century without being lit? It has a name too, and a story, and a careful, almost paradoxical reason it was chosen at all. People hear the word and tense up a little because it's a word that frightens us, and the truth of it is far stranger and far gentler than the fear. The fuel is plutonium, and I know that word just landed, even in the quiet, even at this sleepy hour, with a small weight to it. Plutonium. It carries a particular shadow in the human imagination, and I want to take that shadow gently apart right now before we go any further, because the truth of this particular plutonium is almost the opposite of what that shadow suggests. There are 2 kinds that matter to us here. 2 isotopes, which just means 2 versions of the same element, each with a slightly different number of neutrons in the nucleus, each behaving in a completely different way. One of them you may have heard of in a very different context, plutonium-239, that's the one. That's the kind associated with weapons, with chain reactions, with the terrible compression of enormous energy into a very small space and time. Plutonium-239 is the thing that frightens people when they hear the word, and it frightens them for historically understandable reasons. Voyager runs on the other one, plutonium-238, and the reason it was chosen specifically, deliberately, carefully, is that it is almost completely useless for a weapon. It cannot sustain the kind of chain reaction that makes a bomb. If you tried to build a nuclear device with plutonium-238, you would fail. It simply does not do that. What it does instead, the only thing it does instead, is generate heat. Steady, patient, reliable, relentless heat. It decays slowly, naturally, without any prompting or arrangement. And every time it decays, it releases energy, and that energy shows up as warmth. That is its one trick, and it is an extraordinary one. The full name, if you want the precise form sitting inside those generators right now, is plutonium-238 dioxide. Written as 238PuO2, it's not in metallic form, not loose powder, not anything that looks dangerous in the way a film version of this story might imagine. It's pressed into ceramic spheres, solid, dense, hard, a material chosen partly for its physical properties as much as its radioactive ones. Each of the 3 multi-100-watt RTGs on Voyager holds 24 of those pressed spheres, and across all 3 generators per spacecraft, The total mass of that fuel is roughly 4.5 kilograms, a little less than 10 pounds. You could hold the amount of material that has powered an interstellar mission for nearly 50 years in 2 cupped hands. And when you think about the ceramic form, the reason for it starts to become clear. Plutonium on a rocket is a question that deserves a real answer, not a dismissal. Rockets fail, they have always, sometimes failed, they will always, sometimes fail. The people who built these generators had to answer the question honestly, to themselves and to everyone else. What happens if this rocket doesn't make it? What happens if there's an accident on the launch pad, or a failure in the upper atmosphere, or a re-entry that nobody planned for? The answer they built into the design is the ceramic. Plutonium-238 dioxide in ceramic form is rugged in the specific ways that matter. It's engineered to survive the things a launch accident might throw at it. Not just heat, though it can handle that, but impact. The kind of violent dispersal that might happen if a rocket broke apart. The ceramic spheres are designed to stay intact, to hold together, to not scatter as fine radioactive particles into the environment. The fuel is locked inside the material itself. This is not an accident of manufacturing or a lucky side effect. It's the design. The safety architecture starts with the choice of what form the fuel takes. Ceramic, precisely because ceramic does not do what the fear imagines. So we have our 4.5 kilograms of pressed ceramic plutonium-238 dioxide sealed inside those generators, mounted on the boom out away from the instruments. And now comes the part that always surprises people, even if they think they know this story. Because the question underneath all of this, the question the mechanism has to answer, is how does a material that nobody lit, nobody heated from the outside, nobody did anything to, how does it sit there glowing red hot? The answer is alpha decay. And alpha decay is something worth understanding, even gently, even in the fuzzy way you absorb things when you're half asleep, because it's one of those pieces of physics that is stranger and quieter and more patient than anything invented. The nucleus of an atom is not perfectly stable, as a rule. Most elements we encounter in daily life are stable enough that they'll stay the same for longer than the universe has existed. But some nuclei, and plutonium-238 is one of them, sit in a slightly higher energy state than they'd like. Not dramatically, not catastrophically, just slightly. And over time, in the slow way of physical processes that operate without any hurry at all, they relax toward a lower energy state by releasing a tiny bundle of particles. For plutonium-238, that bundle is an alpha particle, which is just 2 protons and 2 neutrons stuck together, a helium nucleus, if you want a way to picture it. A very small, very dense, very energetic little thing, ejected from the plutonium nucleus with considerable speed. Now, this alpha particle doesn't go anywhere useful. It doesn't escape the generator. It doesn't light anything or burn anything in any conventional sense. It slows down almost immediately because the material around it, the other atoms in the ceramic, absorb it. The alpha particle plows into the surrounding material, loses its kinetic energy in a series of collisions, and that kinetic energy has to go somewhere. It goes into heat. The surrounding material gets warmer. Do this enough times with 4.5 kilograms of plutonium-238, doing this naturally and continuously, and you end up with a fuel that is genuinely, measurably, visibly hot. A pellet of plutonium-238 dioxide glows, not because anything is burning, not because there's an external source of energy, but because the atoms themselves are releasing small bursts of energy as they settle toward a more comfortable state, and that energy accumulates as warmth. Well over 1,000 degrees Celsius in the fuel itself, hot enough to glow visibly red in the dark, hot enough that handling it without protection would be immediately and catastrophically unwise. And yet it requires nothing from outside. No spark, no oxygen, no fuel in the combustion sense, no maintenance. It arrived at this temperature by itself from the inside, from the physics of what plutonium-238 is, and it will stay hot, slowly cooling, for a very long time. At launch in 1977, the thermal output across those three generators, all that heat pouring off 4.5 kilograms of ceramic plutonium, was on the order of 7,000 watts. 7,000 watts of heat. Enough to run a small home's worth of appliances, or to keep a vehicle's engine warm in winter, or to heat a modest room on a cold night. 7,000 watts of heat, sitting on a boom attached to a spacecraft on its way out of the solar system. And the electricity from all that heat? 160 watts per generator, very roughly, times 3. Around 470 watts total at launch. The draw of a few bulbs, as we said. 7,000 watts in, 470 watts out. You can feel the gap already. That gap is the whole story of warmth, but we'll get to it properly in a moment, because first we need to understand how that translation happens at all. How does heat become electricity? There's no turbine in an RTG, there's no steam, no generator in the mechanical sense, no moving parts of any kind. The journey from a glowing plutonium sphere to an electrical current is done by something much simpler and much older. It's done by the Seebeck effect, and the Seebeck effect was discovered in 1821, which means it is over 200 years old. 2 centuries of physics sitting quietly inside the most distant human-made object in existence. Thomas Johann Seebeck was a physicist, and in 1821 he discovered something that sounds very simple when you first hear it. If you take 2 different materials, 2 different metals, or 2 different semiconductors, any 2 dissimilar conductors, and you join them together at 2 points, and you make one of those joints hot and the other cold, a voltage appears. A difference in temperature across a junction of dissimilar materials produces an electrical potential difference. Electricity from heat, not through magnetism, not through motion, not through chemical reaction. Simply from the difference in temperature between 2 ends of a joined pair of materials. This is the Seebeck effect, and it works because electrons in different materials behave differently under heat. When one end of the junction is hot, the electrons on that side have more energy and tend to diffuse toward the cooler side. But because the 2 materials respond differently, they diffuse at different rates, and this imbalance creates a net movement of charge, and a net movement of charge is an electric current. The physics is elegant and quiet and involves no machinery at all. It's temperature itself doing the work. The device built on this principle is called a thermocouple, and the Voyager RTGs contain hundreds of them, tiny junctions of dissimilar material, each one doing this same small trick of turning a temperature difference into a voltage. Wire hundreds of them together in the right arrangement, and the individual small voltages add up into something useful. The specific material chosen for Voyager's thermocouples is a silicon-germanium alloy, abbreviated Sig. Silicon-germanium was selected because it performs well at the particular temperatures involved. Hot enough on the fuel side to give a good gradient, and cold enough on the outer side, facing the vacuum of space, to maintain it. The 2 ends of each thermocouple live in very different worlds. One end touches the heat of a glowing plutonium sphere. The other end faces space. Not just cold space in the ordinary sense, but space at distances from the sun where sunlight barely exists. And here is something counterintuitive and lovely about the design. The colder the outer end of the thermocouple, the better the gradient. The larger the temperature difference between hot and cold, the more electrical potential the Seebeck effect generates. So the frigid emptiness of deep space, well, the very thing that seems like it should be a hostile enemy to a spacecraft, the thing that should make all of this harder, is actually part of the engine. The universe's cold is doing useful work. The darkness and the distance and the near absolute emptiness that Voyager swims through are not threats to the power supply. They are conditions. The RTG works better in deep space, in a real and measurable sense, than it would closer in. There is something almost philosophical in that, though perhaps philosophy is a bit much at this hour. The darkness helps, the cold cooperates. The very extremity of the environment that seems most hostile becomes the thing the machine leans into. You can let that image drift with you if you want. The void pulling the heat out one way so the electricity can flow the other. So we have the Seebeck effect, and we have the silicon-germanium thermocouples, and we have 7,000 watts of heat on one side and the cold of interstellar space on the other. And the result at launch is 470 watts of electricity, which means, and this is the number I want to let sit for a moment, only about 6 to 7% of the heat becomes electricity. 6 or 7%. The conversion efficiency of a thermoelectric generator is brutally, almost comically low by the standards of most machines we build. A good steam turbine can convert 30 or 40% of its heat into useful work. An RTG does 6 or 7. 93% of the heat, the vast majority, the overwhelming bulk of all that energy that plutonium-238 is releasing goes somewhere other than electricity. It goes into the spacecraft, it radiates gently and continuously into the structure and the instruments and the bays and the lines and the propellant tanks. And here, right here, is the inversion that changes everything about how you understand this mission. That 93% is not waste, not in deep space, not in the context of what Voyager actually needs to stay alive. Think about where this spacecraft is. Think about what surrounds it. When Voyager crossed the heliopause, the boundary, where the sun's influence finally gives out and true interstellar space begins, which Voyager 1 crossed in 2012 and Voyager 2 crossed in 2018, it entered a region of space where the sunlight is somewhere between 1/25,000th and 1/40,000th of its strength at Earth. Those numbers are almost too small to picture. Imagine standing in a room where someone has replaced the overhead light with the very faintest nightlight imaginable, and then imagine dimming it another 100 times. At Voyager's distances, sunlight is, for any practical thermal purpose, effectively zero. An unheated object sitting in interstellar space would reach an equilibrium temperature far, far below anything we ordinarily deal with. Now think about Voyager's propellant, hydrazine. Hydrazine is the substance in Voyager's thruster lines that, when fired, allows the craft to adjust its orientation, to point its antenna at Earth, to execute small maneuvers. Without functioning thrusters, Voyager cannot maintain the pointing that keeps its radio dish aimed at our planet, and hydrazine freezes at about 2 degrees Celsius. 2 degrees, just barely below the temperature of a well-chilled refrigerator, barely below the point at which cold water starts to become ice. If those thruster lines and tanks ever drop below 2 degrees Celsius, the hydrazine solidifies. It becomes a gel, then a solid, and the thrusters cannot fire through solid propellant. And if the thrusters cannot fire, Voyager cannot reorient its antenna. And if the antenna cannot reorient, it will slowly drift off the precise pointing needed to reach Earth, and the signal, that fantastically faint signal that already barely reaches us, will go quiet, not fade, not weaken, just stop. The spacecraft will still be out there, still traveling, still carrying its golden record and its instruments and its 48 years of history, but we will never hear it again. 2 degrees Celsius. That is the temperature that ends everything, not a catastrophic failure, not an explosion, not a collision, a gentle, quiet crossing of a threshold that anyone who's ever left a bottle of wine on the porch in winter has already casually exceeded. 2 degrees, and the last human voice in interstellar space goes silent forever. And the thing keeping those lines above 2 degrees Celsius is the heat that the RTGs are throwing off as their so-called waste. The 93%. The fraction that seemed like inefficiency. the part that doesn't become electricity. That heat flows through the structure of the spacecraft. It warms the interior, it keeps the electronic bays at workable temperatures, and it keeps the hydrazine lines, crucial, fragile, irreplaceable, above freezing. The engineers who designed Voyager understood this from the beginning. They weren't apologizing for the low efficiency of thermoelectric conversion, they were using it. The RTG was always doing two jobs. Job one, make electricity to run the instruments and the computers and the transmitter. Job two, keep the spacecraft from freezing. And of those two jobs, in the long run, in the decades-long twilight of the mission, Job 2 turns out to be at least as important as Job 1. Maybe more. You could almost flip the description around and it would be just as true. These are not power generators with a useful side effect of warmth. They are heaters that also happen to make a little electricity. 6 or 7% of the thermal output is the electricity that runs the spacecraft. The rest is the blanket that keeps it alive. 7,000 watts in, 470 out. And the difference, that huge invisible remainder, is what has kept the hydrazine liquid for nearly 50 years in a region of space where sunlight no longer meaningfully exists. It's what has kept the computers from thermal failure. It's what has kept every component of that spacecraft in a temperature range where it can still do its work. The cold of space doesn't threaten the thermoelectric gradient, it improves it. And the warmth that seems wasted is the warmth that keeps the whole thing from freezing solid. The two hostile properties of the environment, the cold and the distance from the sun, are both working in the same direction. The cold makes the electricity better, and the heat that would otherwise just be lost keeps the machine alive. Everything hostile out there has, in this very specific design, been turned into something useful. Take a moment with that if you want, there's no hurry. The spacecraft that has traveled further from Earth than any other human-made object, that floats in a darkness older and emptier than anything our senses were built to comprehend, has never been cold inside. The inside of Voyager, the small, warm cave of electronics and memory and ancient programming, has been kept alive by a process that was old when radio was new, running on a fuel that glows red-hot without a single spark of ignition. And the inefficiency of that process is the reason the craft is still talking to us. This is worth a moment of just sitting with, because when you hear nuclear battery, you probably picture something like a very long-lived version of an ordinary battery, something that stores energy and dispenses it, something that will eventually run flat, a charged thing, depleting. And the word battery technically belongs to this object in the loose way it sometimes gets used, but the reality behind the word is so different from that picture that the word almost misleads more than it helps. Nothing in an RTG is stored in the battery sense. There's no charge to deplete, no stored chemical potential waiting to be released in a controlled reaction. What there is a material that is, by its nature, continuously releasing small amounts of energy as it slowly transforms into something else. Plutonium-238 is becoming, one alpha emission at a time, uranium-234. It's not burning through a reserve. It's changing atom by atom at a rate governed entirely by nuclear physics and not at all by how much work the spacecraft asks of it. The decay happens whether the instruments are running or not. The heat exists whether anyone is using it or not. The plutonium is not working. It simply is what it is, and what it is produces heat as a natural consequence of its existence. This is profoundly different from a battery. It's more like an element that is slowly and inevitably turning into a different element and releasing warmth as it does. The RTG is the device that catches that warmth and does something useful with it. But the warmth doesn't care about the device, it would be there regardless. And because of this, the RTG's decline is governed not by usage but by physics. By two physical processes running simultaneously, both counting down, both inevitable, neither accelerated by how hard the spacecraft works. The first is the half-life. Plutonium-238 has a half-life of 87.7 years, which means that after 87.7 years, half of the plutonium-238 atoms will have decayed. They'll have become uranium-234. And because those atoms are no longer plutonium-238, they're no longer contributing to the thermal output. Less fuel, less heat, less electricity. The decay is slow and steady and predictable, and from this alone you might expect Voyager to lose only about 0.8% of its power per year. 0.8%. At that rate, after nearly 50 years, you'd expect the power to have dropped to maybe 65 or 70% of the launch level. Still substantial, still impressive. But that's not what happened. The decline has been much faster than the half-life alone would predict. And the reason is the second clock, the thermocouples, the silicon-germanium junctions that do the work of converting heat to electricity. They are not permanent. They don't fail suddenly or catastrophically. There's no thermocouple that winks out all at once, but they degrade. Over years and decades, at the temperatures they live at doing the work they do, the silicon-germanium material slowly changes. Some of it sublimes, converts directly from solid to gas at the very surface, molecule by molecule, disappearing gradually into the surrounding vacuum. And the dopants, the carefully chosen impurities that have been added to the silicon-germanium to tune its thermoelectric properties, migrate over time. This is called dope diffusion, the distribution of dopant atoms, which was set up precisely when the thermocouples were made, slowly blurs and smears over decades, reducing the efficiency of each junction. So the thermocouples lose efficiency. Not because the heat source is weakening much, the plutonium is still mostly there, still mostly warm, but because the machinery that converts that heat into electricity is slowly losing its ability to do the conversion. The engine is running, but the alternator is aging. These two declines together, the slow reduction of fuel and the slower degradation of the conversion machinery, add up to a loss of roughly 4 watts per year per spacecraft. 4 watts per year. That number seems small, but remember what we're working with. 470 watts at launch, 4 watts per year. Across nearly 50 years, that compounds. And the result, by the early to mid-2020s, is that each spacecraft is producing somewhere around 220 to 225 watts. Less than half. Less than half of what they had at launch, running from fewer and more tired thermocouples catching heat from a slowly thinning fuel. 220 watts to run everything, the computers, the radio transmitter, the instruments, the heaters for the hydrazine lines, the heaters for the instruments themselves, 220 watts and falling by 4 more every year. And every watt below the launch total is a choice that had to be made somewhere. Something had to give up its share. Something had to go dark so that other things could stay on. This is where the physics hands the story to the people. Because the question of what gets sacrificed and in what order is not a physics question anymore. It's a human one. It's the kind of question that doesn't have a clean answer, only a careful one. And the people who have spent their careers, some of them their entire professional lives, keeping these two spacecraft talking, have been answering it, instrument by instrument and heater by heater, for decades now. The cameras were the first big loss. The imaging systems on both Voyagers, the cameras that took the pictures of Jupiter's Great Red Spot and Saturn's rings and Neptune's blue arc, were shut down after 1990. The last photographs they took were as part of a sequence that has become one of the most recognized images in history. The family portrait, in which Voyager 1 turned back and photographed the solar system it was leaving. The pale blue dot of Earth, suspended in a sunbeam, and then the cameras went off. Not because they failed, because they couldn't be afforded anymore. The power they drew was needed elsewhere. They've been dark for more than 30 years. Voyager has been in the most literal sense, blind for most of its life. Still listening, still transmitting, still reaching, but unable to see, and that's only the beginning of what's been let go. The plasma science instruments, the plasma wave instruments, various subsystems and redundant components, a long, slow list of things that were turned off, not in failure, but in arithmetic. What's reclaimed, redistributed, used to keep the remaining things alive a little longer. And it has continued more urgently in the years immediately before this one. In 2023 and into 2025, NASA engineers have been making what the project team describes as high-stakes decisions, turning off heaters that were protecting still functioning science instruments, letting those instruments get cold, colder than they were rated for, colder than anyone originally believed they would work in, and finding carefully and with considerable relief that they kept working. The instruments exceeded their own rated operating temperatures on the cold side, staying functional in conditions that the original specifications said would break them. Each time this happened, it was a small gift, a few more watts freed, a little more time bought. In 2025, further shutdowns were announced. The cosmic ray subsystem on one craft, the low-energy charged particle instrument on the other, among them. Each shutdown follows the same logic. What is this instrument still teaching us? And is that worth the watts it's drawing, given what those watts could keep running instead? It's a strange and melancholy kind of triage, not a crisis, not a malfunction, just the slow and inevitable arithmetic of an aging power supply and the careful, considered choices of a team that knows exactly how many watts they have and exactly how fast they're losing them. The logic of the order matters. Non-essential heaters go first, heaters that are protecting things that are either redundant or no longer needed. Then redundant systems, then instruments whose best discoveries are likely behind them, whose role in understanding where Voyager is and what it's traveling through has been filled by years of existing data. And last, held as long as possible, the instruments that are doing the thing no other mission can do. The instruments reading the interstellar medium itself, the properties of the space between stars, the plasma environment, the magnetic fields, the cosmic rays that pour through from the galaxy beyond our solar system. That data is irreplaceable in the most literal sense. No other spacecraft has ever been there. No other spacecraft is going to be there for a very long time. These instruments are the only ears we have in the space between stars, and they are kept running last, fed from whatever remains, for as long as the power allows. And the power continues to fall, 4 watts a year, relentless, indifferent. The engineers project with the care that comes from decades of managing exactly this problem that science instruments can likely be kept running into the 2030s. One instrument perhaps on each spacecraft, drawing the minimum of what's available. And then even that becomes impossible. And then the transmitter itself, which requires power to push a signal across 24 billion kilometers of space, faces the same arithmetic. But we're not there yet. And the full shape of that ending and the extraordinary human story of the people managing it is something we'll come to. For now, just hold the image. A ceramic sphere of plutonium-238 dioxide, one of 24 in each of 3 generators, one alpha particle at a time, turning slowly into uranium-234 and releasing warmth it cannot help but release. That warmth, traveling through silicon-germanium junctions 200 years after Seebeck first understood that a temperature difference across dissimilar materials makes electricity, and arriving as power, humble, shrinking, irreplaceable power, at the computers and transmitters and instruments of the most distant object humanity has ever made. While the fraction that isn't electricity, the great warm remainder, the 93% that no thermocouple could capture, wraps itself around the hydrazine lines and whispers to them, "Not yet, not yet, stay liquid, stay above 2 degrees, let us keep going a little longer." In the coldest place we have ever reached, Voyager has never been cold inside. That was always the plan, and it is still barely working. And now we can sit with that for a moment. Because there's something almost philosophical in what we've just described. A spacecraft absorbing the universe's waste, converting its own waste into survival, and slowly spending both. But there's one more dimension to the cold paradox that's worth turning over gently, because it's genuinely strange, and it's the kind of strange that makes more sense the longer you sit with it. The cold out there is not just an obstacle, it is part of the engine. Think about the Seebeck effect for a moment. The silicon-germanium thermocouple junctions, those hundreds of tiny bridges connecting the hot interior of the RTG to the exterior, they don't generate electricity from heat alone. They generate electricity from the difference, from the gap between the hot side and the cold side. The greater the gap, the more current flows. And out beyond the heliopause, beyond the point where the sun's wind finally gives up and interstellar space begins, the cold side of those junctions is exposed to something that Earth never gets to experience. Something very, very cold. Here on Earth, when engineers test thermoelectric devices, they have to work quite hard to maintain a useful cold reference. They use cooling fins, heat sinks, fluid loops. The environment keeps trying to warm up the cold side, and the engineers keep fighting it. But Voyager doesn't have that problem. Voyager has the coldest environment in practical human experience, available constantly, forever, at no cost. The universe itself is the cold side of the thermoelectric junction. Radiative cooling into the black of interstellar space at temperatures that our bodies would find difficult to even conceptualize gives the silicon-germanium junctions the sharpest possible gradient, the steepest possible slope from hot to cold. In a deep sense, the further Voyager gets from the Sun, the better the thermoelectric physics would like to work, or rather, the better it would work if the thermocouples themselves weren't aging. And we'll come to why they are, but the point, the quiet and important point, is that the deep cold of interstellar space is not fighting the RTG, it is working with it. The universe's emptiness and darkness is a collaborator in keeping Voyager powered. That's not a metaphor, that's the physics. So when people imagine the Voyagers freezing in the dark, and it's an easy image to arrive at 24 billion kilometers from the Sun, in a place where sunlight is essentially meaningless, they're picturing something that is both correct and wrong at the same time. Correct in that, yes, there is almost no useful solar energy out there. Wrong in that the cold itself is not the killer. The cold is part of why the lights have stayed on this long. Let's talk about the sunlight figure because it's worth dwelling on. You know how sunlight feels on your face on a summer afternoon. That warmth, that pressure of photons arriving from a star just 150 million kilometers away. As you travel away from the Sun, the intensity of that light falls off with the square of the distance. Not linearly, with the square, twice as far away, 4 times dimmer, 3 times as far, 9 times dimmer. By the time you reach Jupiter, just 5 astronomical units out, sunlight is already 25 times weaker than it is at Earth. That's why the Galileo and Cassini missions couldn't use solar panels past a certain point. The panels would have had to be enormous, impractically enormous, to gather enough of that diminished sunlight to power a spacecraft. Voyager is over 160 astronomical units from the Sun, more than 30 times further than Jupiter. And because of that square relationship, the sunlight arriving where Voyager is right now is somewhere between 25,000 and 40,000 times weaker than what strikes your window on a clear day. We're not talking about dim, we're talking about effectively nothing. A solar panel the size of a football field out where Voyager is would produce something close to nothing useful. A candle in a hurricane, less than that. What this means practically for a spacecraft made of metal and electronics and fuel lines and wires is that there is no external warmth arriving, none. Space around Voyager is not cold the way your refrigerator is cold, or the way a winter night is cold. It is cold the way the absence of heat sources is cold, a radiation sink drawing energy away from anything that has any. If Voyager were a rock out there, an unheated metal box drifting beyond the heliopause, the sun's contribution to its temperature would be close to zero. Its temperature would be determined by how fast it radiates its own energy away into the darkness, and that process doesn't stop. It never stops. In the end, an unheated object in deep interstellar space finds an equilibrium temperature far below the freezing point of anything we care about. Far below the temperature at which electronics work. Far below the temperature at which any propellant stays liquid. This is the situation Voyager would be in if not for the RTGs. And here's where we arrive at the thing I mentioned earlier. The thing that seems almost too convenient, almost too elegant to be true. The hydrazine. Hydrazine is the propellant Voyager uses for its small thruster rockets, not for main propulsion. Voyager has been coasting unpowered for most of its journey, on the trajectory the laws of physics gave it when it swung around Jupiter and Saturn. But for attitude control, for making the tiny adjustments that keep its antenna pointed at Earth, it uses small hydrazine thrusters, little bursts of controlled chemistry, nudging the spacecraft's orientation by fractions of a degree. And those thrusters, and the lines that carry hydrazine to them, have to stay above a very specific temperature. Hydrazine freezes at approximately 2 degrees Celsius, about 34 or 35 degrees Fahrenheit, just barely above the freezing point of water and, in terrestrial terms, a quite mild temperature. A cool autumn morning, the kind of temperature at which you might want a light jacket. In interstellar space, that temperature is an engineering cliff edge. Think about what happens if those lines freeze. If the hydrazine in the tubes connecting the tanks to the thrusters solidifies, the thrusters can't fire. And if the thrusters can't fire, Voyager can't adjust its orientation. And Voyager's antenna, the large dish antenna that sends and receives every signal, every command, every piece of science data, every heartbeat transmission, that antenna is pointed at Earth. It is pointed at Earth right now in this moment as you listen with extraordinary precision, the same precision that has been maintained for nearly 50 years. If that pointing drifts and the thrusters can't correct it, Earth hears nothing. Voyager continues to sail on, the signal continues to be transmitted, but the beam has missed, and we never hear from it again. That's the real deadline, not the battery going flat in any abstract sense. The hydrazine line, 2 degrees Celsius. That's the number. That's the temperature the RTG waste heat is fighting every second across 24 billion kilometers of space in a place where nothing else is above freezing. And the extraordinary fact is that it has been winning for nearly 50 years because the 93% of thermal energy that the thermocouples can't convert into electricity, all that heat that an engineer on Earth might look at and call waste, might look at and wish they could recapture, might look at and see inefficiency, that heat flows through the structure of the spacecraft, into the bus, into the electronics box, into the instrument platform, and along the hydrazine lines. It keeps the fuel liquid, it keeps the thrusters ready, it keeps the antenna aimed. The inefficiency is the survival mechanism. And here is where the 2-clock problem becomes important to understand, because it's not something that most tellings of the Voyager story explain properly. And without it, you can't really understand why the power down is happening on the schedule it is, or what the engineers are actually managing. There are 2 separate processes making Voyager's power fall. They run simultaneously, and they're both irreversible, and they compound each other in the sense that the management of one affects the other. The first clock is the plutonium-238 decay. This one is pure physics, precise and predictable. Plutonium-238 has a half-life of 87.7 years. What that means physically is that after 87.7 years, half of the plutonium-238 atoms in each ceramic sphere will have decayed into uranium-234. They will have emitted their alpha particles, they will have contributed their heat, and then they will be finished. Gone from the fuel pool, permanently replaced by uranium atoms that don't heat the same way, that don't feed the thermoelectric conversion. Now 87.7 years is a long time. The Voyagers launched in 1977. 87.7 years from then is around the year 2065. We haven't reached the halfway point of the plutonium's decay yet, which means from decay alone, the fuel isn't losing half its energy anytime soon. The rate of power loss from pure isotope decay works out to roughly 0.8% per year. In the early years of the mission, the RTGs were losing less than 4 watts of electrical output per year just from the fuel thinning. So why are they losing 4 watts per year now? Why is it so much faster? That's the second clock. And it's more complicated, more mechanical, and in some ways more poignant because it's not written into the laws of physics the way nuclear decay is. It's a consequence of engineering reality, of materials in an extreme environment for an extreme time. The silicon-germanium thermocouples, those hundreds of junctions bridging the hot fuel and the cold space, doing the work that Thomas Johann Seebeck first described in 1821, turning a temperature difference into an electric current. They are not immortal. They were built in the 1970s. They have been operating continuously since 1977. And over those decades, in the heat and vacuum at the junction between a plutonium furnace and interstellar space, they have been changing. There are 2 processes happening to them. The first is sublimation. Some of the materials in the thermocouple junctions, at the temperatures they operate at, slowly vaporize. Not dramatically, not in a visible cloud of vapor, but atom by atom, molecule by molecule. The material at the hot junction migrates. Over a year, it's invisible. Over a decade, it might be measurable. Over nearly 50 years, it adds up. The geometry of the junction changes, the contact quality changes, the efficiency changes. The second process is called dope diffusion. The silicon-germanium thermocouples are semiconductor junctions, and like all semiconductor junctions, they depend on the precise distribution of dopant atoms, impurities deliberately introduced in tiny quantities to give the material its specific electrical properties. At room temperature, those dopant atoms sit where they were put, they don't move. But at thermocouple junction temperatures over decades, they migrate, they diffuse. The precise profile of electrical characteristics that made the junction work optimally in 1977 is not the same profile that exists in the 2020s. The result of both processes is the same. The conversion efficiency drops. The silicon-germanium junctions don't convert heat into electricity as well as they used to. The same amount of thermal energy from the same amount of plutonium produces less electrical output than it did 40 years ago. And crucially, this degradation is not slowing down. It's approximately linear. The thermocouples aren't reaching some stable aged state where they hold constant. They continue to degrade. Every year, the junctions are a little worse than the year before. Every year, a little more of the plutonium's heat passes through them without becoming electricity. When you add the fuel decay rate and the thermocouple degradation rate together, you get the observed figure, roughly 4 watts per year of lost electrical output per spacecraft. 4 watts every year gone. At launch in 1977, the 3 RTGs on each Voyager were producing together approximately 470 watts of electrical power. By the early and mid-2020s, that number had fallen to somewhere around 220 to 225 watts. Less than half. Less than half of the electricity they were designed to produce arriving now, not because anything broke dramatically, not because of a failure or an accident, but because time is patient and physics is relentless, and both clocks, the nuclear one and the thermoelectric one, have been counting down simultaneously. 225 watts to power the computers, the transmitter, the science instruments, and the heaters to keep the hydrazine liquid, to keep the antenna aimed, to keep the heartbeat going. Engineers have known this decline curve for decades. They have plotted it, modeled it, argued about it, and planned around it. The curve doesn't surprise anyone at JPL or at NASA. What it does is constrain them. Every year the power budget gets a little tighter. Every year the available watts have to stretch a little further to cover the same essential functions. And here is where the idea of warmth becomes something more than physics, because as the electrical power falls, so does the ability to run heaters. And as the ability to run heaters falls, the internal temperature of the spacecraft slowly begins to approach that cliff edge. 2 degrees Celsius. Not quickly, not all at once. The spacecraft is well insulated. The RTG itself still produces far more thermal energy than it converts to electricity. Remember, even at current reduced output levels, the waste heat being rejected is substantial, many times the electrical output. But the warmth is not evenly distributed, and not every part of the spacecraft is equally well coupled to the RTG thermal output. And the instruments and electronics and fuel lines at the extremities of the spacecraft get their warmth through a combination of RTG radiation, conduction through the structure, and active electric heaters. When the electric power budget shrinks, those active heaters have to be managed. And when the heaters are turned off to save power for something more essential, the parts of the spacecraft they were protecting begin, gradually, to get colder. This is the heart of the triage that is now underway. And it's the part of the story that moves me most, if I'm honest with you. Because it's not a story about machines failing. It's a story about choices, about what you keep and what you sacrifice and in what order, about the ethics of an ending. We'll get there. But it's worth staying here in this cold arithmetic for a little longer. The question that every year brings is the same question. With the watts we have, what can we power? And the answer keeps getting smaller, not because the engineers are losing control, because they have been in control of this decline for longer than some of them have been alive, and their management of it has been extraordinary. But because the physics doesn't pause for anyone, and 4 watts per year is 4 watts per year, and no amount of clever engineering gets those watts back. Let me give you a sense of the actual numbers in physical terms. 225 watts is not much. Think about what you have on right now in the room or on the pillow where you're listening. A phone charging draws maybe 10 or 15 watts. A bedside lamp might draw 40. A laptop somewhere between 30 and 60. If you added up every low-power device in a reasonably frugal modern home, 225 watts would cover maybe a few rooms' worth of modest usage. And that is the entire power budget of the most distant object humanity has ever made. Everything, every computation, every radio transmission, every scientific measurement, every heater, has to fit inside that number. And it has to keep fitting as the number keeps shrinking. Now, 225 watts sounds modest, but there's something else happening that makes it even more constrained than you might think. The transmitter, the radio that sends Voyager's signal back to Earth, uses a significant portion of that budget, not the majority, but a meaningful portion. And that signal, traveling across more than 24 billion kilometers, arrives at Earth as something almost incomprehensibly faint, roughly a tenth of a billionth of a watt. That's approximately 10 to the negative 22 watts, a number so small that most ways of saying it don't quite communicate how small it is. 10 to the negative 22 watts. The engineers at the Deep Space Network, working with their enormous dish antennas in California and Spain and Australia, catch that signal. They filter it out of the cosmic background noise, they reassemble it, they confirm it, and they decode it. A 20-plus watt transmitter aboard a spacecraft running on the electricity equivalent of a few dim light bulbs, broadcasting from 24 billion kilometers away. And what arrives is something fainter than almost any signal we routinely work with. This is what the RTG is sustaining, this faint voice in the dark, and in the background the two clocks run. The plutonium decays at its steady, irreversible rate. Atoms that were fuel becoming atoms that are not, the ceramic spheres growing incrementally lighter in their radioactive load, their heat output infinitesimally but measurably lower. And the silicon-germanium junctions continue their slow, microscopic deterioration, subliming, diffusing, losing a little more of their ability to translate that heat into the electrons that keep the lights on. 4 watts per year, less than half the launch power remaining, the curve pointing in one direction. And the thing that has kept Voyager from the cold all this time, the warm embrace of that inefficient, generous heat, wrapping around the hydrazine lines and whispering not yet. That warmth itself is part of what's being rationed now. Not all of it. Not yet. But the margin is thinning. The envelope is smaller. And the engineers are responding to it with a care and a precision that I find sitting with it genuinely moving, because they have always known this was coming. From the day the spacecraft launched, everyone who worked on the RTGs knew the half-life, knew the thermocouple behavior, knew the power curve. They designed the mission to last as long as possible, and they built the RTGs knowing that the fuel would outlast the thermocouples in terms of what set the pace of decline. They prepared for a long, slow, managed descent. And for nearly 50 years, the teams at JPL have been executing that descent, methodically, carefully, with a kind of stewardship that is rare in any human endeavor. The question now is not whether the power will run out. It will. The question is, of everything that Voyager is doing, what is kept last? And to understand why that question is so carefully considered, you need to understand what Voyager is still seeing, still measuring, still sending back, because Voyager 1 and Voyager 2 are not just historic artifacts coasting through space. They are, right now, the only human-made instruments in interstellar space. They are the only things we have ever built that are actually out there, beyond the heliopause, beyond the sun's influence, in the true interstellar medium. And the measurements they send back from that place are, in a scientific sense, irreplaceable. No other mission has ever reached interstellar space. New Horizons is heading that way, but it hasn't arrived. The Voyagers are, for now, the only 2 data sources we have for what the space between the stars is actually like. The magnetic fields, the particle environment, the plasma, the cosmic rays arriving not from the sun, but from the wider galaxy. These are measurements you cannot make from Earth, cannot make from near-Earth orbit, cannot make from anywhere closer than the heliopause, and both Voyagers are in the middle of those measurements, still gathering, still transmitting. This is the terrible arithmetic of the triage. Every instrument that goes dark is a set of measurements that will never be taken again. There will not be another mission to interstellar space for many decades, perhaps not in any of our lifetimes. What the Voyagers know, what they are measuring right now in the interstellar medium, is knowledge that has no substitute. And yet the power budget requires choices, so the engineers make them, with great care, with documented logic, with a triage order that reflects, in some deep sense, a judgment about what Voyager's remaining life is for. The cameras are the most famous example of what was already sacrificed. The imaging science subsystem, Voyager's Eyes, was shut down after 1990. The last image taken was the famous family portrait, the sequence that included the pale blue dot, Earth, as a tiny mote of light in a sunbeam against the black. After that, the cameras were powered down, not because they failed, because keeping them on would have cost power and memory that couldn't be justified for a spacecraft beyond the solar system where there is nothing to photograph. The decision was made deliberately, and it was made over 30 years ago. For more than 3 decades, Voyager has been flying blind. No images, just data streams from instruments measuring things you can't see, particle energies, magnetic field strengths, plasma densities, wave frequencies. The cameras have been off for longer than many of the people managing the mission now have been working on it. And the cameras were only the beginning. Over the decades following, other instruments were shut down as the power budget required. Plasma spectrometers, redundant systems, equipment whose data was no longer unique or whose operational demands cost more than the mission could justify. Each shutdown was a negotiation, a technical review, a hard conversation about what the remaining power was for. What has been kept running through all of this are the instruments that are unique to Voyager's position. The instruments that are measuring interstellar space in ways nothing else can. The cosmic ray detection, the magnetic field measurement, the plasma wave detection, the low-energy charged particle instruments. These are the sensors telling us what it is actually like out there, in the medium between the stars where no other spacecraft has ever gone. These are the last things to go. These are what the triage is protecting. So the logic runs like this. The available power goes first to the computers, and because without the computers, nothing works. It goes to the transmitter, because without the transmitter, even if everything else worked, we'd hear nothing. It goes to the propellant heaters, because without warm hydrazine, the antenna can't be aimed, and again, we'd hear nothing. And after those absolute essentials, what remains is divided among the remaining science instruments, each drawing its own small number of watts, each returning its irreplaceable measurements of interstellar space. As the power keeps dropping, 4 watts per year, the 2 clocks ticking together, the total left over for science instruments keeps shrinking. The engineers look at the power budget and ask which instrument stays on. They protect the ones doing the most irreplaceable science. They turn off the ones whose data, while valuable, is less unique, or whose operational demands can no longer be justified against the budget. And they turn off heaters. This is the part that, when I first fully understood it, struck me as the starkest illustration of the situation. There are heaters throughout the spacecraft. Small electric heaters keeping various components within their rated operating temperature ranges. Some of those heaters protect instruments that are still running, and in recent years engineers have been turning those heaters off, one by one, and watching what happens. The gamble is this. If you turn off the heater protecting an instrument, the instrument gets colder. How cold? Cold enough to fail? Or will it keep working beyond its rated temperature in the cold that the RTG alone, without the heater supplement, provides? Nobody knows for certain in advance. These are instruments built in the 1970s, operated far beyond their design life, and now exposed to conditions outside their design specifications. Whether they survive the cold without their heaters is something you find out by doing it. And what has happened in recent years has been remarkable. Instruments that engineers feared might fail in the cold have kept working, operating below their rated temperatures in conditions the designers never intended them to experience. The surviving science instruments have continued functioning, continued measuring, continued transmitting. It's as if the spacecraft itself has found a kind of resilience that wasn't fully anticipated, as if the hardware, like the mission, has simply refused to give up on the schedule anyone planned. But this is not infinite. The margin of warmth that the RTG waste heat provides without heater supplements is itself shrinking as the fuel decays and the thermocouples age. Every year the baseline temperature a little colder. Every year the buffer between where the spacecraft is and where the hydrazine cliff edge is a little thinner. The instruments that are surviving now in the cold without their heaters are surviving because the RTG still produces enough waste heat to keep them above failure temperature. As that waste heat continues to diminish, the window will close. Things that work today may not work in 3 years, or 5, or 7. This is why the projection into the 2030s is a projection, not a date. It depends on the actual degradation rate of the thermocouples, which has followed a curve but is not perfectly predictable. It depends on which instruments prove most resilient to cold. It depends on decisions not yet made about which heaters to sacrifice next, and in what order. The engineers have models, and the models have ranges, and the ranges say something like 1 or 2 instruments probably into the early to mid-2030s, and then the instruments one by one will go dark, and then the transmitter, and then the heartbeat. That is the shape of the ending that the 2 clocks are writing. And in the middle of all of this, in the last few years, there was a moment that reminded everyone just how fragile and how extraordinary the whole thing is. In late 2023, Voyager 1 began sending back corrupted data. The telemetry was garbled, not just wrong, but strange, the kind of wrong that suggests the problem isn't a software glitch, but something in the hardware. The mission team, most of them working with a spacecraft computer, they know better than any other humans alive. A spacecraft computer built on 1970s architecture, running 1970s assembly code, carrying 70 kilobytes of onboard memory, which is to say less memory than a single short email, began the slow work of diagnosis. The signal takes over 22 hours to reach Earth from Voyager 1. Send a diagnostic command 22 hours before you know if it arrived. Receive a response, another 22 hours before it gets back. Every exchange is a minimum of 44 hours, a 2-day conversation. Every test, every probe of the spacecraft systems, every attempt to narrow down the location of the fault is conducted across that impossible lag. And the team found it. A corrupted memory chip in the flight data subsystem, the part of the computer responsible for packaging and sending the science and engineering data. Not just any memory, a specific chip. And not just found, they found a workaround. They relocated the code around the failed chip, rewrote the memory layout of a 1970s spacecraft computer via radio signals crossing 22+ hours of space in such a way that the corrupted region was bypassed and the system resumed functioning. From interstellar space, across 44+ hours of round-trip communication, they fixed a memory chip fault in a 47-year-old computer and brought the spacecraft back to full communication. Some of the people on that team came out of retirement to help, because the number of humans who still know Voyager's code, who learned assembly language for that specific computer architecture in the late 1970s and early 1980s and have maintained that knowledge across their careers, is very small. When the spacecraft needs that knowledge, JPL finds the people who have it, and some of those people are in their 70s now, having spent decades in other work, called back for a spacecraft they helped build before some of their current colleagues were born. Human knowledge, perishable, specific, irreplaceable, sustaining a machine in interstellar space. The signal that Voyager sends back, the signal that those engineers pored over for months, trying to understand what had gone wrong and then right again, arrives at Earth at approximately 10 to the power of -22 watts. That's the received signal strength. A tenth of a billionth of a watt captured by the enormous dish antennas of the Deep Space Network in California, in Spain, in Australia. Their receivers tuned to frequencies so quiet that almost nothing on Earth radiates at them, listening for a transmission that started as 20 or more watts from a spacecraft 24 billion kilometers away and arrived as almost nothing at all. Almost, but not nothing. Enough. Still enough for the Deep Space Network to hear it and decode it and pass it along to the people who are waiting. While you're asleep tonight, those antennas will be listening. The same spacecraft that was launched when the current engineers were children, or before they were born, will be transmitting its quiet stream of measurements from the space between the stars. and the deep space network will catch it, and the data will be processed. And somewhere in that data will be something that no one has ever measured before, from a place no one has ever been. That is what the two clocks are slowly ending. And there is one more thread in this story, the fuel itself, and what the loss of its production meant for the future. Plutonium-238 is not mined from the ground. It is produced in nuclear reactors through a process of neutron bombardment of Neptunium-237. It requires a specific kind of reactor operation and a specific kind of processing infrastructure. In the United States, that production ran from the early years of the space program through the late 1980s, supplying the Voyagers and Pioneer and Galileo and Cassini and New Horizons. And then, in 1988, it stopped. The reactors that produced it were repurposed or decommissioned. The production lines were shut down. The expertise began to scatter. For roughly 2 decades, the United States had no domestic source of new plutonium-238. The nation that built the Voyagers, that had used RTGs to power missions across the outer solar system, that had demonstrated over and over that radioisotope thermoelectric generators were the only practical power source for missions beyond Jupiter. That nation could not make the fuel for a new one. The plutonium-238 in the Curiosity Mars rover, which launched in 2011, was partly sourced from what remained in stockpiles and partly from Russia. It was a sobering illustration of how fragile the capability was. If you wanted to build a new Voyager, you couldn't simply build it. You'd need the fuel, and the fuel had to come from somewhere. And for 2 decades, there was essentially nowhere. The Department of Energy eventually restarted plutonium-238 production. The facility doing it is Oak Ridge National Laboratory in Tennessee, the same Oak Ridge that was part of the Manhattan Project, that has been part of American nuclear history since the 1940s. The restart was announced in the 2010s, and production of new fuel has been slowly building toward the volumes needed to support future deep space missions. It takes years to build up meaningful quantities. The process is slow, the infrastructure expensive, the expertise requiring careful reconstruction. The fuel in Voyager's RTGs, those ceramic spheres of plutonium-238 dioxide, pressed and fired decades ago, glowing red-hot in their generators since 1977, is in a real sense heritage material. There is no going back and making more of exactly that. The physical material has been doing its work, atom by atom, alpha particle by alpha particle, for nearly half a century. The United States lost the ability to make it for 20 years and is only now rebuilding toward the production rates that a vigorous outer solar system exploration program would require. You cannot recharge an RTG, you cannot replace its fuel mid-mission. Whatever Voyager had at launch is what it has now, minus the atoms that have already decayed, minus the efficiency lost to aging thermocouples. The supply is closed. The account has been drawing down since 1977, and the ledger will eventually reach zero. It will reach zero slowly. The half-life is 87.7 years, and the spacecraft launched in 1977, and in purely nuclear terms, the fuel is barely past a quarter of its decay cycle. In purely nuclear terms, there is still most of a half-life left in those ceramic spheres, but the thermocouples don't care about nuclear terms. They have their own timeline, their own degradation, their own irreversible drift away from the efficiency they started with. And it is the thermocouples, more than the fuel, that are writing the schedule of the ending, 4 watts per year. From 470 down to 220-something across the years since 1977 to now. And the curve continuing downward, flat and merciless and perfectly predictable, toward the number where the last instrument cannot be kept on, and then toward the number where the transmitter cannot be kept on, and finally toward the long silence. The hydrazine line is the last gate. When the last watt that can be spared for the propellant heaters can no longer keep those lines above 2 degrees Celsius, the thruster won't fire. The antenna drift that is always being corrected, the slow wobble of a spacecraft 47 years old in the currents of the interstellar medium will go uncorrected. The beam will wander, and Earth will lose the signal, not because Voyager stopped, because Voyager couldn't aim anymore. And then Voyager will continue, outward. At roughly 17 kilometers per second for Voyager 1, at a slower but still extraordinary pace for Voyager 2. Into the interstellar medium, through it, beyond any region we have ever mapped or imagined in detail. In roughly 40,000 years, Voyager 1 will make a close approach to a star called Gliese 445 in the constellation Camelopardalis. It will pass within about 1.6 light-years of it. Probably, the orbital mechanics of stars shift over that kind of time, but roughly, in 40,000 years, and aboard it, needing no power, storing no data, making no measurements, asking nothing of the RTGs or the thermocouples or the hydrazine, will be the golden record. But that is where the next part of this story goes. We're not finished yet with the deliberate choices, the triage in progress, the human hands still on the controls of the most distant object our species has ever made. The power is still on, the signal is still reaching Earth, the deep space network is still listening, the 2 clocks are still running. So let's stay here for a moment, here in the present tense, here where the power is still on. Because what happens between now and that long silence is not passive. It is not the drifting decline of a machine that simply winds down on its own. It is managed. It is deliberate. It is, in the most literal sense, a series of choices made by human beings on Earth across a gap of 22 or 23 hours each way, about which pieces of a dying spacecraft to keep alive and which to let go cold. It is triage, and triage has a logic. Think about what that word means, the original meaning, from the French, from the field hospitals, where medics had to make fast decisions about who could be saved and who could not, and in what order to act. You don't treat the hopeless case first. You don't treat the walking wounded first either. You treat the ones who will survive if you act, and who will not survive if you don't. You make the hardest kind of calculation, to cruelty, not indifference, but a disciplined love for what can still be preserved. That is what the engineers at NASA's Jet Propulsion Laboratory have been doing, slowly, over decades. A triage that has unfolded not in minutes, but in years. Each decision documented, each shutdown a deliberate sacrifice. And it started long before the 2020s. The cameras went first, not because the cameras were unimportant. They had given us some of the most extraordinary images in human history, the rings of Saturn seen up close for the first time, the moons of Jupiter resolved from blurry points of light into actual worlds, a volcanic plume erupting on Io, caught in a single frame that made the scientists in the room gasp out loud. Those cameras. But by 1990, the cameras had done their work. There were no more planets ahead. The outer solar system flyby was complete, and Voyager was heading into the dark between the stars, where there was nothing to photograph, nothing near enough to resolve, nothing a camera could capture that would tell you anything new. And cameras are power-hungry things. The imaging systems, the Vidicon tubes, and the associated data processing drew watts that could no longer be justified. So in 1990, just before Voyager 1 took the image that Carl Sagan had requested, the one that would become the pale blue dot, the image of Earth as a mote of dust suspended in a sunbeam taken from a distance of about 6 billion kilometers, the decision had already been made. The cameras would be shut down. That image, and the mosaic of the solar system family portrait it was part of, would be the last. After that, Voyager would fly blind. No images, no photography, just data about fields and particles and the invisible structures of space itself. And that was fine because that was what the instruments that remained were built to measure. The cameras had done their job. Now the particle detectors and the magnetometers and the plasma science instruments would do theirs in the interstellar medium, where no spacecraft had ever been before. Voyager has been effectively blind for more than 30 years now. That is easy to forget. When people think of Voyager, they often think of those photographs, Jupiter, Saturn, the pale blue dot. But the spacecraft that is out there right now, crossing through interstellar space, has not taken a photograph in over 3 decades. It is listening, not looking. And the instruments it has been using to listen have been going dark, one by one, ever since. The logic of the triage order is straightforward when you understand what each instrument does and what it costs. The engineers work through categories. First, you turn off heaters for components that are not actively returning science. Why heat something that isn't producing data? The heater for an already shut down instrument is pure waste, watts consumed to keep warm a piece of equipment that is no longer doing anything. Those go first. They're the easiest cuts. Nobody argues for them. Then you look at redundant systems. A spacecraft like Voyager has, in many cases, backup components, a spare sensor here, a redundant circuit there, that were included in the 1970s because electronics failed more often then, and redundancy was survival. But you don't need the backup running continuously. You can keep it available without powering it, or you can simply accept the risk and shut it down entirely to free the watts. So redundant systems go quiet. Then come the harder decisions, the science instruments themselves. And here the triage gets genuinely painful because these are not redundant systems. They are the reason the spacecraft exists. They are what Voyager was sent to do. The question the engineers have to answer is not simply which instrument draws the least power, though that matters. The question is, given where Voyager is, given what it can still see, given what we still don't know about interstellar space, which measurements are still producing information that cannot be obtained any other way, which instruments are returning irreplaceable data, and which have, in a sense, already told us what they have to tell. That is a scientific and philosophical judgment as much as an engineering one, and it has been made slowly instrument by instrument over the course of years. The plasma spectrometers, which measure the properties of charged particles in the space around the spacecraft, have been central to Voyager's mission in interstellar space because the plasma environment of the interstellar medium is genuinely different from the solar wind, and Voyager's instruments have been measuring that difference in real time since the heliopause crossing. These are instruments that cannot be replaced by any Earth-based observation because you cannot measure the interstellar medium from Earth. You have to be there. The magnetometers have continued working, returning data about the magnetic field structure of interstellar space, data that has already overturned several assumptions about how the heliosphere boundary actually behaves. The cosmic ray subsystem and the low-energy charge particle instruments measure different populations of energetic particles, some coming from the Sun, some from galactic sources. And in interstellar space, the balance between them shifts in ways that are scientifically profound. They tell us about the structure of the galaxy itself, in a small but real way, from a vantage point we have never had before. Every one of these instruments has a power cost, and as the RTGs continue their slow decline, at roughly 4 watts per year, the engineers have had to make choices. Not theoretical choices, real ones. In 2023 and 2024 and into 2025, those choices became acute. NASA announced a series of shutdowns that were, in their own way, extraordinary. Not just turning off redundant systems or sleeping heaters, but turning off heaters for science instruments that were still operating, accepting that the instruments would now be exposed to temperatures far below what they were rated to survive on the gamble that they were hardier than the specifications said, because the specifications were written conservatively in the 1970s by engineers who could not know how these components would actually behave after 45 or 47 years in space. And here is the thing, the gamble paid off. The instruments kept working, cold beyond their rated limits, exposed to temperatures that should, by the book, have degraded their performance or killed them outright. They kept returning data. They are tougher than anyone officially promised they would be. That is not luck. That is the cumulative result of extraordinarily careful engineering, compounded by the simple, strange fact that space is very, very still. There are no vibrations in deep interstellar space, no wind, no weather, no thermal cycling from a nearby star, no microgravity fluctuations from a passing body. Voyager coasts in a kind of absolute mechanical silence. And things that do not move, things that do not flex and expand and contract repeatedly, last longer than things that do. The engineers in the 1970s built these components to survive the launch and the planetary flybys, which involved real stress. But once past all of that, out in the deep, Voyager has been in the most mechanically benign environment imaginable. Cold, still, undisturbed. It is still dying, though, slowly, mathematically. The thermocouples are still sublimating. The plutonium-238 is still decaying. The 4 watts per year are still being lost, and the choices are still being made. In 2025, NASA announced the shutdown of additional instruments. The cosmic ray subsystem on one spacecraft and the low-energy charged particle instrument on the other. Each one freed a few watts. Each one narrowed the range of science that Voyager could still do. Each one was a small grief, acknowledged and then set aside because the alternative was to lose everything sooner. And the priority at the end of every calculation, the thing the engineers will sacrifice the last instrument to protect, is not science at all. It is the transmitter. And behind the transmitter, the hydrazine heaters. Because if the antenna can still aim, if the propellant lines are still above 2 degrees Celsius, if the signal can still reach Earth, even at 10 to the power of minus 22 watts, even as a whisper from 24 billion kilometers away, then there is still contact. There is still the possibility of another command, another adjustment, another piece of information. The moment the hydrazine freezes, that possibility ends. Not gradually, not slowly. It ends the moment a thruster fails to fire when it's needed to correct the antenna's aim. The beam wanders, the connection breaks, and there is nothing anyone on Earth can do to restore it. So everything else is sacrificed to keep those propellant lines warm. Every instrument, every heater for every other component. All of it, in the end, subordinate to one goal: keep the hydrazine liquid, keep the antenna aimed, keep the signal coming. The projection, as of the mid-2020s, is that the Voyagers may be able to maintain at least one science instrument operating into the late 2020s or perhaps into the 2030s. After that, the instruments will all go dark, one by one, until there are no more. And then for some period, difficult to calculate exactly because thermocouple degradation is not perfectly linear, and because the exact thermal behavior of the spacecraft interior depends on factors that cannot be modeled with perfect precision from 47-year-old data. For some period, the transmitter will keep running, and the Deep Space Network will keep listening, and Voyager will keep sending a signal that contains nothing except the fact that it is still there. And then that too will stop. There is something worth dwelling on in that projection. The fact that the engineers cannot give you an exact date, not because they haven't tried, and not because the physics is unknown, but because they are managing a system that is beyond its design lifetime by decades, composed of components whose exact condition they cannot directly inspect, operating in an environment that has never had another spacecraft in it to compare. They are flying something they can see only as data, something they can touch only through a 22-hour conversation delay, something that is slowly becoming more unknowable even as they work to understand it. They are doing this with 70 kilobytes of onboard memory. Think about that for a moment. 70 kilobytes. The email you might have gotten today, the one from a colleague with 3 attached documents and a company logo in the signature, is probably larger than the entire addressable memory of Voyager's computer. A single photograph on your phone is larger. A few seconds of low-quality audio is larger. And inside those 70 kilobytes lives the software that manages the spacecraft's attitude, processes the science data, handles the communication protocols, manages the heater circuits, monitors the power levels from the RTGs, executes the commands that arrive across the solar system. All of it within a space that a modern computer would fill in a fraction of a second with housekeeping data it doesn't even notice generating. The team that maintains this software is small, smaller than you might expect for the most distant human-made object in existence. And some of them are not young. Some of them came out of retirement specifically because they are among the last people alive who understand the assembly language code that Voyager runs on, the actual binary instructions written in the 1970s that tell the spacecraft what to do. The younger engineers can learn it, and they do, but the institutional memory, the deep understanding of why a particular subroutine is written the way it is, what edge case it was solving, what a particular behavior in the data actually means, some of that lives in people who were working on this mission before some of the current engineers were born. That knowledge transfer is its own quiet emergency. A slow one, but real. And it matters because Voyager requires active maintenance of a kind that people don't always appreciate. It is not coasting passively. Commands go up, software patches are written and uplinked, adjustments are made. The triage decisions are enacted through actual code changes sent across 22 hours of empty space and confirmed across 22 hours of return signal. Every time the engineers make a change, they have to wait nearly a full day to find out if it worked. That reality became brutally vivid in 2024 when Voyager 1 began sending back corrupted data. Not silence, not nothing. Data, but garbled, wrong, inconsistent in ways that didn't make sense. The spacecraft seemed to be alive, seemed to be functioning, seemed to be receiving and responding to commands. But the data it was returning was not coherent science or engineering telemetry. It was noise, or worse than noise. It was data that looked like it might mean something, and then didn't. The diagnosis took months of analysis across that 22-hour gap, months of careful testing, months of trying to understand what had gone wrong inside a computer that was traveling at 17 kilometers per second through interstellar space and could not be opened, could not be physically inspected, could not be rebooted in the way you would reboot a laptop by holding down a button. What they found eventually was that a chip in the flight data subsystem, the component responsible for packaging the spacecraft's engineering and science data before transmitting it, had failed. Specifically, a small region of memory had corrupted. The code that was supposed to live in that memory was damaged, producing garbled output. The solution was elegant and extraordinary. They could not fix the chip. The chip was not fixable, not from Earth, not from anywhere. What they could do was relocate the code, move it, piece by piece, to other regions of the flight data subsystem's memory that were still intact, updating references and addresses as they went, testing each piece before moving to the next. Doing all of this in 70 kilobytes of 1970s assembly language across a 44-hour round-trip conversation. It worked. By the spring of 2024, Voyager 1 was returning coherent data again, a dead memory chip on a 50-year-old computer 24 billion kilometers from Earth, fixed by a team of engineers using the equivalent of a postal service with a 22-hour delivery time. That is what it means to fly this spacecraft in its final years, not passive monitoring, active, difficult, high-stakes problem-solving, conducted under constraints that have no parallel in any other engineering domain. And the signal that carries all of this while the commands going out, the data coming back, arrives at Earth with a power of roughly 1/10 of a billionth of a watt. That is approximately 10 to the power of negative 22 watts, a number so small it is almost meaningless as a number. You need the deep space network to catch it. The large radio dish antennas, some of them 70 meters across, pointed with extraordinary precision at a point in the sky that is not where Voyager appears to be, but where it will be in 22 hours when the light from the dish reaches it, accounting for the motion of the spacecraft and the motion of the Earth and the finite speed of the signal itself. The Deep Space Network catches a whisper from 24 billion kilometers away. A 20-watt transmitter, a transmitter drawing on the last scraps of power from 3 slowly dying RTGs, producing a signal that arrives at Earth with less energy than almost any signal that any radio telescope routinely detects. And yet they hear it, reliably, every day. That too is a form of engineering miracle, though a quieter one than the RTG itself. And somewhere in those signals, in the numbers that the remaining science instruments are returning, in the magnetic field measurements and the particle counts, and the plasma wave data, there is information that exists nowhere else in human knowledge. Information about the interstellar medium as it actually is, measured from inside it by a probe that crossed a boundary, the heliopause, that no human instrument had ever crossed before Voyager 1 did it in 2012 and Voyager 2 did it in 2018. What those crossings revealed surprised people. The interstellar medium is not what the models predicted, not exactly. The magnetic field doesn't orient the way many theories suggested it would. The boundary between the solar wind and interstellar space is sharper in some ways and more complex in others than the simplest models had anticipated. The density of electrons outside the heliopause behaved in ways that told scientists something about the structure of interstellar space that they had not known before. These are not dramatic discoveries in the sense of headlines or immediate applications. They are slow science, careful science, the kind that goes into papers and models and revisions of models, the kind that eventually, years or decades later, shows up as a corrected understanding of how the galaxy works, how the solar system sits within it, how the boundary between our star's domain and the broader interstellar space actually functions. And it is only possible because Voyager is there, because those RTGs, those 3 multi-hundred-watt generators on their deployable boom, have kept a small collection of instruments alive for long enough to reach the one place in the universe where these measurements can be made. There is one more thing worth knowing about the fuel that made this possible, about the plutonium-238 itself. The United States stopped producing it in 1988. For nearly 3 decades, the stockpile that powered Voyager and Pioneer and Galileo and Cassini was a finite, dwindling resource. When NASA wanted to power New Horizons, the mission to Pluto, they had to use plutonium-238 that had been recycled and repurified from old RTG material that had already been used and recovered. The margins were tight. There were missions that could not be proposed or had to be redesigned because there simply wasn't enough fuel to power them. It was not a classified crisis or a secret failure. It was a bureaucratic and budgetary one. The reactors that produced plutonium-238 for NASA were shut down as part of broader decisions about the Department of Energy's facilities, and nobody at the time prioritized keeping them running for the sake of deep space exploration. And so the capability quietly vanished until the missions that depended on it started running short. The Department of Energy, working with Oak Ridge National Laboratory, restarted plutonium-238 production in the 2010s. It is being produced again now, but the gap is real. And it means that the plutonium-238 inside Voyager's 3 RTGs, still decaying, still glowing, still producing heat at a temperature well above 1,000 degrees Celsius inside those ceramic spheres, is in a sense irreplaceable. Material from an era of production capacity that lapsed for almost 30 years. Fuel from a world that no longer exists. That realization carries a certain weight. The Voyagers were built in a moment when the infrastructure to build them existed, and some of that infrastructure has since gone away and had to be painfully rebuilt. The Curiosity rover on Mars and the Perseverance rover on Mars both run on RTGs, which means the PU-238 restart was not academic, it was necessary. But the particular fuel in Voyager, pressed into those ceramic spheres in the 1970s, launched in 1977, is its own kind of artifact. And now we are very close to the end of the story. Not Voyager's end, that, as we've said, is effectively never, on any time scale that matters to human beings. The spacecraft will coast outward for billions of years. But the end of the part of the story that involves contact with Earth, the part of the story where people are still making decisions, still managing the triage, still listening to that whisper of signal from the most distant thing our species has ever made. The last instrument will go dark. The engineers don't know exactly when. The projections suggest somewhere in the late 2020s to mid-2030s for the last science measurements, and then some further period, perhaps into the late 2030s or 2040s, though this is uncertain, before the transmitter itself can no longer be powered, and when the transmitter goes, the signal stops. Not because Voyager dies, Voyager doesn't die, it keeps going. It keeps carrying its instruments, its computers, its empty hydrazine lines, its deployable boom with 3 cold and silent RTGs, their plutonium still decaying, still glowing at some fraction of their original temperature, producing heat that has nowhere useful to go anymore, onward into interstellar space. And on the spacecraft, needing no power at all, asking nothing of the RTGs or the thermocouples or the hydrazine or the computers, there is the golden record. It is a 12-inch gold-plated copper disc. It carries sounds and images, greetings in 55 languages, music from many cultures, the sound of rain and surf, and a mother's first words to a newborn child. It carries a diagram explaining how to read it, instructions encoded in the physics of the hydrogen atom, because hydrogen is the most common element in the universe, and any civilization advanced enough to recover this object should know its properties. It was never designed to be found. Carl Sagan, who championed it, knew perfectly well that the odds of any civilization ever intercepting a spacecraft tumbling silently through interstellar space were vanishingly small. It was not a practical communication. It was a gesture, a statement about what kind of species built this thing, what they valued, what they wanted to say about themselves at the moment they first sent something beyond the solar system. And when the last instrument goes dark and the transmitter falls silent and Earth stops hearing Voyager, the golden record will still be there, spinning slowly with the spacecraft's very gentle rotation, gold-plated against the corrosive nothingness of interstellar space, which is not very corrosive at all, which is in fact the best preservation environment imaginable. Scientists estimate it could remain legible, that is physically intact, and readable to whoever might find it, for 1 billion years. 1 billion years. The RTGs will be cold long before that. The decay heat of plutonium-238 follows its 87.7-year half-life, and in 10,000 years the fuel will be essentially inert. In 100,000 years, the plutonium that once glowed at over 1,000 degrees Celsius will be cool metal, indistinguishable in temperature from the surrounding spacecraft, but the record will still be there, intact, patient, carrying the sounds of a world that 1 billion years from now may itself be unrecognizable. The nuclear battery will have long since stopped. The record it helped carry to the stars will be the last thing still there. There is something in this that I find genuinely hard to hold in my mind all at once, the chain of it. The way a piece of physics discovered in 1821 by Thomas Johann Seebeck, a temperature difference across a junction of 2 dissimilar materials, produces a current, a phenomenon he observed in a laboratory, probably never imagining it would one day generate electricity from the cold of interstellar space. The way that piece of physics was built into a generator, packed around a fuel that no one had bothered to synthesize until the middle of the 20th century, bolted onto a spacecraft designed to fly past gas giants and then keep going, pointed outward, for as long as physics allowed. The chain from Seebeck's laboratory to interstellar space took about 150 years, and the chain from interstellar space to right now, to you, wherever you are, in a bed or on a couch or in a dark room somewhere, listening to this. That chain is the deep space network, still catching that 10 to the negative 22 watt whisper, still converting it to numbers, still routing it to engineers who are still, right now, thinking about the next shutdown, the next what to save, the next gamble about how cold an instrument can get before it stops working. The most distant thing our species has ever made is still, at this moment, alive. Still sending. Still arriving. And when it finally stops arriving, when the hydrazine lines cross that 2-degree threshold and the antenna drifts away from Earth, and the signal that has been crossing 22 hours of space every day for nearly 50 years simply isn't there anymore, when the deep space network listens, even then something of it will keep going, outward. Through the interstellar medium, past the regions we have only just begun to map, toward Gliese 445 in the constellation Camelopardalis, 40,000 years from now, a close approach in cosmic terms, though still more than a light year away. And beyond that, into spaces we have no names for, around stars we haven't catalogued, through the thin and ancient gas between the arms of the galaxy. A gold-plated disk, sounds of rain, a child's first cry, greetings in 55 languages to no one in particular, or to anyone, to everyone, to whatever form of awareness might one day drift close enough and curious enough to reach out and pick up a small metal object tumbling in the dark. We started tonight with a paradox. The coldest place humans have ever reached, the interstellar medium beyond the heliopause, where Voyager 1 has been since 2012, where Voyager 2 followed in 2018, 160 astronomical units from the Sun, 24 billion kilometers, a place where sunlight is a 25,000th of its strength at Earth, and the equilibrium temperature of an unheated object is far below the freezing point of everything. The coldest place we have ever sent anything, and inside it, a spacecraft that has never once been cold, because of a lump of plutonium-238 pressed into ceramic spheres, glowing at over 1,000 degrees Celsius, slowly decaying by alpha emission, slowly surrendering its heat to hundreds of silicon-germanium junctions that translate a temperature difference into electricity. Not efficiently, only 6 or 7% of it, but that isn't the point. The point is that the waste, the other 93%, is heat. Gentle, steady, patient heat that has been keeping the electronics warm, keeping the hydrazine liquid, keeping the antenna aimed at a blue dot 22 light hours away for 47 years. The inefficiency was the design, the waste was the warmth. And the warmth kept it alive long enough to cross a boundary no human instrument had ever crossed, to return data from a place no spacecraft had ever been, to tell us something true about the shape of our solar system's edge and the nature of the space beyond it. And it is still there, still going, still for now, still on. If you've been drifting tonight, that's all right. The ideas will have settled somewhere the way things do when you're half asleep. Not as facts you can recite, but as a kind of texture, a sense that the universe is stranger and more carefully engineered than it usually seems. A piece of physics from 1821, a fuel that glows red hot and needs no reactor, no moving parts, no charging. A spacecraft running on 70 kilobytes and maintained by people who came out of retirement because they are among the last who remember how it works. A team sending commands across 22 hours of empty space and waiting 22 more to find out if they worked, and a signal right now crossing that distance, a tenth of a billionth of a watt, arriving every day. Wherever you are tonight, in whatever corner of the world, with whatever lamp is still on or already off, that signal is coming in. The Deep Space Network is listening. The engineers will check the data in the morning. The triage continues. If this slow journey through the physics of warmth and the quiet heroics of a dying spacecraft brought you some peace tonight, a gentle like or subscribe means a great deal to this small, sleepy channel. Small creators like me rely on your support to keep these nights going. And if you'd like to leave a note before you drift off, where in the world are you listening from tonight? And what time is it in your corner of the dark? I would love to know. The Night Watch has the dark covered. You can let go now.